Hello folks, so I'm going to try this out, this whole recording, doing a video type thing, and see if it works. If it doesn't, then I'll just use PowerPoints like Miss LeBrun has done, okay? So I'm going to start with 7.5 because that's what we would have done on Thursday last week. So friction and motion, so nothing we haven't seen before, sort of just boxes or particles moving on an inclined plane. Okay, so just a little diagram to help you out. If it mentions forces and acceleration, then you want to use F equals ma. If it mentions speed, distance, or time, then you want to use SUVATs. Okay, and just bear in mind, again, like we've been saying before, if it says rough, then you know friction's involved. Just read it carefully. It might take sort of like 2 or 3 times to read through, but that's okay. So I'm going to go through 2 examples. The first one I'm going to go through quite slowly. The second one, if you want to pause it and have a go yourselves and then check that you've done it right, then that's fine. You're in charge of this, okay? I'm merely facilitating. So, first one, and I have pre-drawn the inclined plane because I found out that drawing straight lines on a tablet does not work, and they would look even worse than my usual diagrams. Although, wait for it. So, the first one says a particle is held at rest on a rough plane, which is inclined to the horizontal at an angle alpha, where tan alpha is 0.75. Okay, so if we label ourselves up first, so they've told us that this is going to be alpha. Sorry, I need to get my pen. Apologies. Right. Okay, so this bit is alpha. If you want to draw yourself a little triangle so you can sort of properly find out what it is, that's fine. If you just want to use inverse tan, then I completely understand. So that will be alpha. If it's 0.75, it will be 3/4. Okay, and then I can just use Pythagoras and find out that that is 5. Lovely. So back to our original diagram. So particles held at rest. So I'm going to just draw a nice little particle sitting on my plane. And then they've told me that it's rough, so I know that friction's going to be acting in the opposite direction from the motion. So it hasn't said anything's pushing it up, so I'm assuming it's just being brought down by the weight. So friction's going to be going this away. Apologies for the wobbly lines. And then the weight is acting downwards. They haven't told me what the mass is, so I'm just going to put mg. Okay. And again, if you want to label your little angle there, then that's fine. And then, of course, a reaction force acting perpendicular to the plane. Lovely. And then I'm just going to remind myself that they told me mu is 0.5. And then we're good to go. Lovely. Cool. So if I want to find the acceleration of the particle, so I know it's moving sort of down the plane, so in this direction. So I would want to resolve parallel if I was trying to find this. However, I don't know what friction is. So it might be a good idea. So if we remember, friction is equal to mu r. We've been told what mu is. We don't know what r is, but we could work it out. So we could work it out by resolving perpendicular. Okay. So if I resolve perpendicular, I've got r. And then it's not moving, so it must be in equilibrium. So I can say r is equal to mg cos alpha. Okay. And then I could simplify that a tiny bit because I know that cos alpha is going to be the adjacent over the hypotenuse. So it's going to be equal to 4/5. Lovely. Right. So now I know what r is. Now I can resolve parallel. So if I resolve sort of going parallel and using the motion, so going down the plane, so because I'm going to use F equals ma. So I would say my forces, I've got the weight pulling it down the plane, so mg sine alpha, and then that is going to be minus friction, and then that's going to be equal to, so it's actually moving, so we're going to use mass times the acceleration, which we'll find out in a moment. Okay, so I can now replace my friction with mu times my reaction force, so mg sine alpha minus 0.5 times mg 4/5 equals ma. So I can divide by m for each one. So if I then work out sine alpha at the same time, so sine alpha, remember, is going to be opposite over hypotenuse. So I've got 3/5 of g minus, so 0.5 times 4/5 is going to be half times 4/5, so 4/10 g equals a. So then if I simplify this, so I've got 0.6 g minus 0.4 g, so I've got 0.2 g equals the acceleration. So I know that the acceleration, if I pop that into my calculator, so 0.2 times 9.8 to two significant figures is going to be 2.0. Okay, so that's part A. So they just wanted the acceleration. Okay, so part B asks for the distance it slides down. So it mentions distance. So hopefully your brain should be going, SUVATs. Okay, so if we write down what we know, so we know that t is equal to 2. We know that u is equal to 0 because it starts from rest. We know that the acceleration was 0.2 g. I'll leave it like that because that's as exact as we can get it at the moment. And then they want us to find out what s is. So if you have a little think, which SUVAT uses t, u, a, and s? Hopefully you've realised it's our favourite. So s equals ut plus half at squared. Oh my goodness, I don't know what happened there. Okay, so if we substitute in all our bits and pieces, I've got 0 times 2, so 0, plus a half times 0.2 g times by 2 squared. So that's going to give me, so half and the 2 cancel, so I've got 2 times that, so 0.4 g, which if we pop that into our calculator, is going to give us 3.9 meters to 2 sig fig. Okay. Okay, so I'm going to go through example 10 now. So if you want to sort of pause it and have a go at it at your own pace, then that's absolutely fine. You can then press play and check if you got it right, or fast forward me, whatever suits you. So I'm going to go through this same pace as the one before. So I've got a box of mass 2 kilograms. Okay. So that's being pushed up a rough plane. Okay, so nice box. It's being pushed up a rough plane by a force, a horizontal force. So this is the important bit. So horizontal force is going that way. So it's 25 newtons there. We've got a reaction force. So it doesn't fall through the plane. We've got friction opposing the motion. So if it's going to be pushed up the plane, then friction is going to act against that. We've got a 10-degree angle here. And then they've told us mu is 0.3. They've also told us that the mass is 2 kilograms. So I know that the weight is going to be 2g. And if you want to, again, label your angles up, so that's going to be 10 degrees. That's going to be 10 degrees. Using alternate angles, of course. I think that's about it. Trust me that that's a 3. Cool. Right. So we can now get going. So very similar to the last problem we did, we're trying to find the acceleration. So we want to resolve sort of parallel because that's the way that the box is moving. However, we don't know what the reaction force is, so therefore we don't know what the friction is. So first thing we should probably do is resolve perpendicular to the plane. Okay, so we can say we've got the only sort of upward force is the reaction force. The rest of the forces are sort of going towards the plane. So we've got it being equal to 25 sine of 10 degrees. You can draw yourself a little triangle if that helps you out. Plus we've got our 2g cos 10 degrees. Okay. So I'll leave that as it is for the time being. We can sort of simplify it a bit in a moment. So if we now resolve parallel, so very similar to what we did before, this time because it's sort of going upwards, I'm going to take that as my sort of positive force. otherwise I'll have to make the MA bit negative as well, and that'll just get messy. So I'm going to say I've got my push force, so I've got 25, and this is going to be cos 10 degrees. And then I've got acting opposite it, I've got my weight and my friction, so minus my friction minus my 2g sine 10 degrees this time. And then we know that that is going to be equal to MA, so 2A in this case. Okay, so now we can start simplifying a little bit. So I've got 25 cos 10 degrees, give myself a bit more room this time, minus, so I can substitute my reaction force times by my coefficient of friction. So 0.3 times by 25 sine of 10 degrees plus 2g cos of 10 degrees minus 2g sine of 10 degrees equals 2a. Cool. Right, so that looks very messy. However, everything here we can simplify, and then we can just divide the whole thing by 2 in a moment. Okay, so what I can do to sort of make life a bit easier is I could probably collect all my cos terms and all my sine terms, and then I can just pop it all into the calculator. So I've got 25 minus, so 0.3 times 2 is going to be 0.6g. So all of that lot times by cos of 10, which is not one of those nice angles, so you'd have to pop that in your calculator. And then I've also got my sine one, so I've got minus 0.3 times 25, so 7.5, and then minus, so that will become a plus 0.6g sine of 10 degrees. Okay, and then that whole thing equals 2a. So if I pop all this in my calculator, I can say I've got 14.124 ... equals 2a. So if I divide both sides by 2, I've got a equals 7.1 meters per second squared, and that is to 2 sig fig. So it's accelerating up the plane at 7.1 meters per second squared. Okay. Just a quick note before you sort of close the video. You don't really have to do this interim step. They've just done it in the textbook. I would personally, if I had a calculator and you guys didn't mind me sort of faffing around and wasting time, sort of talking to you, I would calculate sort of 0.6g and the cos 10 and the sine 10, and I would write it down so they can see all my workings. But seeing as I run out of space and I don't want to sort of talk too long, I've just copied what they've done in the textbook to make life easier. Okay, if you've got any questions, please do ask. Otherwise, your turn. So exercise 7E, and I'll try and post the next video. If not by tomorrow, then definitely by Thursday. Okay, thanks guys. Bye.